Now, step 2, move everything to one side. So moving here, AV minus lambda V, which is equal to 0. And here, step 3, yes, we are just going to factor out V. That is requires converting lambda to lambda I. So, which it just makes us like A minus lambda I multiple by V, which is equal to 0. Here, of course, you would have asked this one, why lambda I? Because actually, A minus lambda is a matrix minus a scalar, which is undefined. We need to subtract a matrix from a matrix. So, we use lambda I, that is a diagonal matrix with lambda on the diagonal. So, this is matrix shifting. And here this exact left side of AV, that is a matrix vector multiplication, which is generally produces a complete new vector pointing in new direction. And here this right side, this lambda V is a scalar vector multiplication, which only stretches or compresses the vector along its original direction. Notice that the dashed arrow point in the exact same direction as the solid arrow. They are only longer. This is the defining property of eigenvectors. The matrix stretches them without rotating them. So V1, of course, the lambda 1, kindly just see here the eigenvalue lambda 1 is 1.38, meaning A stretches it by a factor of 1.38. And from this we construct a rank 1 signal and noise model. Yes, of course, which is mathematically specified as x is equal to f multiplied by dou transpose plus epsilon. And dear friends, yes, here this exact f is a single latent factor, yes, shared across all variable. And w, yes, random loadings, how strongly each variable depends on the factor. And last epsilon, yes, a small independent noise. So here let me just define the matrix. So here A is a 2 into 2 matrix, and here we have the eval and ecalc, that is eigenvalue lambda 1 and lambda 2, and here eigenvector, that is matrix V, whose columns are eigenvectors. And dear friends, kindly just observe, here is the constructing of the diagonal matrix. So this matrix contains only scaling factor along its diagonal. So when we just do lambda, yes, we just get lambda, which is equal to lambda 1, 0, 0 and lambda 2. So this is what the exact. So this matrix contains only scaling factors along a diagonal. So here it is what the core identity, that is AV, which is equal to V multiplied by lambda. So when we just make it mathematically, kindly just observe, V, of course, we have two vectors, V1 and V2. So yes, a tall matrix or wide matrix, a square matrix and rank deficient. And here we are going to construct the matrix, that is A transpose multiplied by A. So here it defines the two main key properties. That one, it is all about the symmetry. Yes, of course, A transpose multiplied by A, the whole transpose, which is equal to A transpose multiplied by A. And second, it is for quadratic form. So kindly just observe, X transpose multiplied by A transpose multiplied by A whole multiplied by X, which is equal to A multiplied by X whole transpose multiplied by A multiplied by X. So here, yes, the square norms of A multiplied by X, that is greater than or equal to 0. So this immediately implies all eigenvalues are non-negative. A transpose is essentially free. You just swap row and column indices. And here for symmetric matrices, we never need to compute V inverse. We simply use V transpose. This is faster, more stable and more memory efficient. And in data science, the matrix we eigendecompose are almost always covariant matrix, which are symmetric by definition, as like kindly just observe C, which is equal to X transpose multiplied by X. So this simplification applies to virtually every PCA computations you will ever run. So if you know your matrix is symmetric, instead of this, kindly just use, of course, np.linearalgebra.eigh of A. Because here H stands for Hermitian, that is the complex generalization of symmetric. And here this EIGH, yes, this is very faster, more numerical stable and returns eigenvalues stored in ascending order. Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, today we are going to discuss on eigendecomposition, which is one of the most powerful and beautiful ideas in all of linear algebra. It takes a square matrix and reveals its fundamental structure, that is a set of special direction, which we just say eigenvectors. An associated scaling factor, yes, that is what eigenvalue. That together tells us everything about what the matrix does. And yes, dear friends, here it is what a simple looking equation. A multiplied by V, which equals lambda multiplied by V. It looks small, but this single equation powers, yes, principal component analysis, noise reduction, data compression, graphic analysis, dynamical systems, yes, of course, a lot and lot. And this exact equation, yes, when matrix A multiplies a special vector V, the result is simply that same vector scaled by this number, that is lambda. Here the vector V is an eigenvector and the scale lambda is its corresponding eigenvalue. Finding all such pairs, that is lambda and V, is what eigendecomposition is all about. And dear friends, of course, there is a prerequisite also. Yes, you should be comfortable with matrix multiplication, determinants, the null space, a matrix rank, and we will also use the concept of matrix shifting. And dear friends, in this session, we will uncover, yes, what eigenvalues and eigenvector really mean and why eigendecomposition works only for square matrix, the geometric interpretations of stretching without rotating. The very first thing to know about eigendecomposition is its scope. Yes, it apply only for a square matrix. Difference, you can't eigendecompose a 3 into 5 matrix or a 100 into 7 matrix. You can just make only, that is M into my M matrix can be eigendecomposed. Because an eigenvalue equation, yes, AV, which is equal to lambda multiplied by V, requires that a matrix vector product AV produces a vector with the same dimensional as V. And here, if this A, yes, if it is this A, if it is an M into N matrix, so with M which is not equal to N, then AV is an M vector while V is an N vector. That cannot be equal. So here every M into M matrix has exactly M eigenvalue, that is counting multiplicities, and M corresponding eigenvector. So for an example, if I just specify 2 into 2 matrices has 2 eigenvalue eigenvector pairs. And to the same, if it is an 100 into 100 matrices, yes, it has 100 pairs and so on. And dear friends, of course, kindly just observe for and non-square matrix, yes, they can be also decomposed, but using singular value decomposition. Yes, we will be discussing it later in next session. Difference, the most intuitive way to understand eigenvector is geometrically. Yes, when a matrix multiplies a vector, it generally does two things. One, it just rotates, that is changes direction, and scales, that is changes length. But for certain special vectors, that is eigenvectors, the matrix only scales them without changing the direction. And yes, of course, that is what mathematically specified, that is AV, which is equal to lambda multiplies V. And here this exact left side of AV, that is a matrix vector multiplication, which is generally produces a complete new vector pointing in new direction. And here this right side, this lambda V is a scalar vector multiplication, which only stretches or compresses the vector along its original direction. So here from this equation, yes, for this particular vector V, the complex matrix multiplications acts like simple scalar multiplication. Okay, let me just discuss that by using this code. So yes, dear friends, this exact script construct a geometric demonstration of how a linear transformation that is represented by a matrix. So here it is A, acts differently on eigenvectors and a non-eigenvectors too. So here S, it is a matrix A, which is a 2 into 2 matrix, symmetric matrix, which guarantees real eigenvalues, orthogonal eigenvectors. And here exactly this was the one computes eigenvalues and eigenvectors. Yes, dear friends, eigenvalues lambda 1, lambda 2 and corresponding eigenvectors, yes, stored as column. And yes, as I specified mathematically, AV, which is equal to lambda multiplied by V. And here we just displace our eigenvalues and eigenvector numerically. And kindly just observe, dear friends, this exact EVAX. So this extracts the first eigenvector, that is column-wise storage. Here we just start our vector preparation. So for eigenvectors, that is for scaled for visualization. So here V1 and V2. So eigenvectors are scaled purely for plotting clarity. And scaling does not change direction, which is the key property of eigenvectors. Kindly have a note. And here non-eigenvectors too. Yes, here kindly just observe W1 and W2. Here W1 standard basis vector along x-axis, and for W2, yes, normalized arbitrary direction. And dear friends, these are not aligned with eigenvector, so they will behave differently under this matrix A. Now let me just frame our plotting, yes, for visualization. So here we are just going to create two subplots. Okay, so two side-by-side plots. Left, of course, it is for eigenvectors, and right, of course, it is for non-eigenvectors. And here this exact left panel, yes, kindly just observe, it computes the transformed vector AV. And here we have the solid arrow, that is original vector, and a dashed arrow for transformed vector AV. And dear friends, kindly just have an observation. Yes, AV lies on the same line as V, and only magnitude changes. And yes, to this equation, here no rotation, only scaling, that is stretching or shrinking. And here we just go for the right panel. Yes, dear friends, kindly just observe. Here we have the exact AW is not parallel to W, the same transformation, but here AW is not parallel to W. Direction changes, geometric rotation and scaling. Of course, it demonstrates AW that is not equal to lambda W. For visual encoding, yes, we have across both the plots, kindly just observe, yes, we have arrows for horizon vector, and yes, a circular marker for original vector and square marker for S vector, and to the same, both the things are there, and a solid line for before transformation, dashed line for after transformation. And here we have, kindly just observe, yes, equal scaling preserves geometric correctness, grids and axis improves interpretability. And yes, dear friends, actually here we have a printed statement. Yes, eigenvector, that is left stay aligned, non-eigenvector right rotates. So this summarizes the core linear algebra principle. Okay, let me just execute and observe the output. And here it's the exact visualizing output. Left panel, it just shows the eigenvectors. So here the solid arrow shows two eigenvectors V1 and V2. So before multiplication of A, okay, the dashed arrow shows the resultant after multiplication. Notice that the dashed arrow point in the exact same direction as the solid arrow. They are only longer. This is the defining property of eigenvectors. The matrix stretches them without rotating them. So V1, of course, the lambda 1, kindly just see here the eigenvalue lambda 1 is 1.38, meaning A stretches it by a factor of 1.38, and lambda 2, that is V2, has eigenvalue as 3.62, meaning A stretches it by factor of 3.62. Both eigenvalues are positive and greater than 1, so both eigenvectors get longer. And here towards the right panel, kindly just observe it is for non-Eigenvectors. So the solid arrow shows two arbitrary, that is non-Eigenvectors. After multiplication by A1, the dashed arrow point in different directions than the originals. So the matrix both rotated and scaled these vectors. So this is typically behavior. Most vectors are not Eigenvector. And dear friends, a matrix has infinitely many vectors it could act on, but only m special direction for an m into m matrix where it acts like a simple scalar. So those direction encodes the matrix fundamental geometric personality. So here, yes, this exact code is not just plotting vectors, it is visualizing the geometric meaning of eigendecomposition. And here, why eigenvectors are fundamental in PCA or stability analysis, differential equation, and quantum mechanics. Difference in this section, yes, we are just going to discuss on statistical interpretation, mainly on principal component analysis. In data science, the most common application of eigendecomposition is what this principal component analysis. Here PCA answers the question, what are the most important directions of variation in a multivariate dataset? The idea is simple but powerful. Given a dataset with many variables, that is what the columns. So we compute the covariant matrix, a symmetric matrix that captures how every pair of variables covaries. So then we eigendecomposition with covariant matrices and mathematically specified as C, which is equals to V lambda V transpose. Dear friends, the exact eigenvectors V are the principal component, that is the direction in the data space that captures the most variance. And the eigenvalues lambda tells us how much variance each direction captures. A screen plot displays the eigenvalues in descending order. The shape of the screen plots reveals the structure of the data. If the dataset is dominated by one nature pattern, the first eigenvalue will be much larger than the reset. So if there are several independent patterns, there will be several large eigenvalues before the drop off. Okay, let me just discuss it by using the code. So this exact script simulates two different data generated process and uses screen plots, that is eigenvalue spectra, to reveal their underlying structure via PCA. So here kindly just observe, dear friends, yes, we have fixes randomness for consistent result, and we create two side-by-side plots. That is left, of course, scenario A, and right by scenario B. So here we just go for that scenario A. Yes, kindly just observe this is one dominant latent factor. And here we are just going to have our data generation. Yes, kindly just observe. And from this, we construct a rank 1 signal and noise model. Yes, of course, which is mathematically specified as X is equal to F multiplied by dou transpose plus epsilon. And dear friends, yes, here this exact F is a single latent factor, yes, shared across all variable. And W, yes, random loadings, how strongly each variable depends on the factor. And last epsilon, yes, a small independent noise. And here it is what the exact computes covariant matrices. Of course, here it is what the 15 into 15 we have the variable. So 15 into 15 covariance matrix, and extracts the eigenvalues and short descending order. And here, yes, dear friends, of course, each bar, that is variance explained by the principal component. And kindly just observe, here we just measure how much variance is captured by the first principal component. And of course, it is expected to be within 70 to 95%, and as explained by PC1. And here we just go for scenario B, and here exactly, kindly just see here, these are the exact data generations. So this creates a block structure that, of course, kindly just observe, for the variable 1 to 5 depends on the factor 1, the variable 6 to 10 depends on the factor F2, and the variables 11 to 15 depends on the factor F3. So mathematically it is specified as like x, which is equal to f1 dou 1 transpose, f2 dou 2 transpose, and f3 dou 3 transpose plus epsilon. And yes, dear friends, here we have the covariance and eigenvalues. So here it just shows that 3 eigenvalues we have, and yes, here we just explains the variance. Yes, it just measures the variance captured by the first 3 component. And yes, let me just execute and view the result. So when on just viewing these plots, kindly just observe, dear friends, here this scenario A, yes, it simulates a data sets with all 15 variables are driven by a single common factor plus small noise. And the screen plot shows one dominant eigenvalue towering over the rest. So this tells us the data is essentially one-dimensional and all variables move together. Think of it like 15 different cryptocurrencies prices that all go up and down with Bitcoin. And this is how it was specified that a data is effectively one dimension, and here PCA will compress it with minimal information loss. And here the screen plot shows a sharp elbow after the first component. And here when on just going towards the scenario B, kindly just observe, dear friends, it simulates a data sets with 3 independent subgroups. 3 independent subgroups of 5 variable each. So the screen plot shows 3 large eigenvalue, then a sharp drop. So this means the data has 3 independent dimensions of variation. Think of stocks from 3 different industries, maybe tech or healthcare or energy, that moves together within each industry but independently across industry. And here the screen plots is one of the most informative single figure in data science. And here when we just go towards this, kindly just observe, dear friends, there's 3 independent clusters of correlated variables. Yes, weak correlations between the clusters. And here this shows 3 large eigenvalues, remaining eigenvalues are small. And as I have already specified, yes, data is approximately 3-dimensional. PCA identifies 3 dominant direction, and here screen plot shows an elbow after this 3rd component. So from this plot, yes, it is understood that scenario A, that is the left plot, one tall bar, rapid drop off. That implies a strong global correlation, single underlying driver. And here towards the scenario B, that is the right plot, 3 tall bars, then drop off, which implies multiple independent structure and a clustered relationship. So from this exact code demonstrate a fundamental principle of principal component analysis. Yes, dear friends, eigenvalues of the covariant matrix reveal intrinsic dimensionality. Large eigenvalue meaning structure, and small eigenvalue it would be noise. So if data has k latent factor, covariant matrix is approximately rank k, and first k eigenvalues are large, remaining eigenvalues are near 0. And yes, with this practical implementation, dimensionality reduction also we have just discussed, that a scenario reduces to 1 dimension and scenario B reduces to 3 dimension. So identifying number of principal components, and it detect latent structure also, diagonalize correlation patterns also. And with this exact scenario of largest eigenvalue and scenario of top 3 eigenvalues. So here the scenario A, yes, variance concentrated in 1 component, and scenario B, variance distributed across 3 components. So yes, this exact code summarize 1 shared factor, 1 dominant eigenvalue and single structure in scenario A, and 3 independent factor, 3 dominant eigenvalue and 3 structure in scenario B. So the screen plot serves as a diagnostic tool that converts covariant structure into an interpretable visual structure of the data latent geometry. Dear friends, till now we understand what eigenvalues and what eigenvector represents. But here the question, how do we find them? The derivation starts from the eigenvalue equation and applies a sequence of logical steps. each building on concepts from the earlier sessions. So this is the exact one of the most elegant derivations in linear algebra. So yes, kindly just observe. Let me just start with the step 1. Yes, start with an eigenvalue equation, that is AV, which is equal to lambda V. Now step 2, move everything to one side. So moving here AV minus lambda V, which is equal to 0. And here step 3, yes, we are just going to factor out V, that is requires converting lambda to lambda I. So which it just makes us like a minus lambda I multiplied by V, which is equal to 0. Here of course you would have asked this one, why lambda I? Because actually A minus lambda is a matrix minus a scalar, which is undefined. We need to subtract a matrix from a matrix. So we use lambda I, that is a diagonal matrix with lambda on the diagonal. So this is matrix shifting. Now this step 3 says that V is a null space of A minus lambda I. Since we execute the trivial solution, V is equal to 0. That is, the 0 vector is never considered an eigenvector. And here the matrix A minus lambda I must be singular. So only singular matrix has non-trivial null space. And dear friends, of course, we have already know that singular matrix have a determinant of 0. That is determinant of A minus lambda I, yes, which is equal to 0. So this equation is called the characteristic equation, and the polynomial you get by expanding the determinant is the characteristic polynomial. And dear friends, for an m into m matrix, this is polynomial of degree m in lambda. So it has exactly m roots, that is by the fundamental theorem of algebra. So giving as m eigenvalues. So let me just discuss that by using this code. So this script derives and verifies the eigenvalues of 2 into 2 matrix using both analytic formula and numerical computation, while highlighting key algebraic properties. This exact script derives and verifies the eigenvalue of 2 into 2 matrix using both analytic formula and numerical computation, while highlighting key algebraic properties. So yes, dear friends, here is the matrix definition. So we have the matrix A, which is equal to 1, 2 and 3, 4. Okay, and here of course it just explains the characteristic polynomial, that is for a generic matrix, if we just have AB and CD, okay, the eigenvalues satisfied, kindly just observe determinant of A minus lambda I, which is equal to 0. So here determinant of A minus lambda, B, C, D minus lambda, which is equal to A minus lambda multiplied by D minus lambda minus BC. And with this expanding, kindly just observe, dear friends, on simplifying this, we just get lambda square minus A plus D lambda plus AD minus BC, which is equal to 0. From this we just get trace, that is the sum of eigenvalue. So here it is trace of A, which is equal to 1 plus 4, which is 5. And the determinant, yes, the product of eigenvalues. So here determinant of A, which is equal to 1 multiplied by 4 minus 2 multiplied by 3. So which is equal to minus 2. So the characteristic equation here is, kindly just observe, let I just take it here. So lambda square minus 5 lambda minus 2, which is equal to 0. And solving this by using the quadratic formula, okay, so we are just going to have the value of lambda 1 and lambda 2. Okay, so let me just evaluate it, and with this we are just going to make a numerical verification by using NumPy, so which it just computes the eigenvalue using a numerical algorithm. And here all closed, yes, it just verifies equality, that is within floating point tolerance. And we have here the exact fundamental identities. Yes, sum of eigenvalues and product of eigenvalues. Okay, so yes, and here let me just execute and verifies the result. And of course, we have already identified the exact characteristic polynomial. Yes, kindly just observe. Here we just have lambda square minus 5 into lambda minus 2, which is equal to 0. And by using quadratic formula, kindly just observe. So lambda, which is equal to 5 square minus 4 into minus 2, which is equal to 25 plus 8, which is 33. And here, if I just want to go with lambda 1 and 2, so 5 plus or minus square root of 33 divided by 2. So numerically, we just get lambda 1, yes, it would be as like 5.37, and lambda 2, yes, it would be minus 0.3723. So that 8 was, we just got it here. Numerical algorithm, it just computes the eigenvalues, and of course both are equal. So here it is the exact fundamental identities. Dear friends, the script verifies two important variants. Yes, one is sum of eigenvalues by the trace. Yes, summation of I, which is equal to 1 to m lambda sub I, which is equal to trace of A. And the second one, it is all about product of eigenvalues, that is product from I, which is equal to 1 to m of lambda sub I, which is equal to determinant of A. And here we just get, yes, this is at 5, and here we just get this value as minus 2. So yes, that is what we just obtained here. So sum of roots, which is trace, and product of roots, that is the determinant. And dear friends, here trace measures total scaling effect along principal directions. And here determinant measures area scaling, that is including orientation flip if negative. And for this matrix, one eigenvalue is positive, that is stretching in one direction. And one eigenvalue, it is in negative, that is reflection plus scaling in another direction. So this exact example illustrates eigenvalues encode intrinsic transformation behavior. That is, the matrix can be understood as stretching along one direction, flipping and compressing another along another direction. So this exact code summarize, that is walk through the full pipeline. So construct a matrix, derive characteristic polynomial, solve analytical, that is quadratic formula, and verify numerically. So confirm invariant relationship, that is trace and determinant. So it demonstrates that eigenvalue are not just computational artifacts, they are tightly constrained by fundamental algebraic properties of the matrix. In this session, we are just going to discuss on how to find eigenvector. Dear friends, once we have the eigenvalues, finding the eigenvector is conceptual straightforward. Each eigenvector V live in the null space of the matrix shifted by its eigenvalue. Mathematically, V sub I belongs to null space of A minus lambda sub I times I. That is, every eigenvector lives inside the null space of its shifted matrix. And dear friends, think of it this way. The eigenvalue is like a key and the matrix is like a lock. You insert the key, that is lambda sub I, into the matrix by shifting, that is A minus lambda sub I times I, and the door open to reveal the eigenvector hiding in the null space. Okay, let me just discuss this by using the code. So dear friends, actually this exact script computes eigenvector by explicitly solving the null space problem. Yes, the null space problem mathematically specified. Yes, A minus lambda times I multiple by V, which is equal to 0. So for each eigenvalue, and then verifies the result numerically. So let me just define the matrix. Yes, here we have the matrix. Yes, it is a symmetric, guarantees real eigenvalue and orthogonal eigenvector. And here, yes, of course, we have the eigenvalue. numerical Python. And here we just go for the step 1. Yes, this is the exact core idea where we just specified, yes, the null space A minus lambda times I. Yes, for each eigenvalue of lambda, we are just going to compute the shifted functionalities. And this produces a matrix whose null space contains the eigenvector. And here we have, kindly just observe, dear friends, yes, this is the code logic for solving the null space. Yes, this implements a manual null space solution, and here, yes, it just uses the first row equation. Yes, of course, it just specify as like mathematically A multiplied by V sub 1 plus B multiplied by V sub 2, which is equal to 0, which implies, yes, V2 which is equal to minus A divided by B multiplied by V sub I. And here, yes, if we just set this V sub 1 which is equal to 1, yes, to obtain a concrete vector. And it handles edge cases where division would be unstable. And yes, dear friends, here we have the normalization. Yes, it converts eigenvector to unit length, and it is mainly important for numerical stability, consistent comparisons. So this exact verification step, it just makes the check A multiplied by V, which is equal to lambda V. So yes, here we have the exact comparative statement with numpy, and this numpy returns eigenvector as column. They may differ by, of course, a scalar multiple, as like sign flips. So this is expected because eigenvectors are not unique. And here this V and C multiplied by V represents the same direction. Okay, so let me just execute and view the result. So here we just discussed, dear friends, kindly just observe. Here we have the matrix A, that is 1, 2, 2 and 1. And here we are able to identify the value of lambda 1 and lambda 2 as with help of characteristic polynomial. Yes, you can verify the characteristic polynomial here. It is lambda square minus 2 multiplied by lambda minus 3, which is equal to 0. And here, yes, with this functionality, we are able to identify that is lambda 1, it is 3, and lambda 2, it is minus 1. So yes, we just got the exact eigenvalues here. And with this, let me just compute the shifted matrix. So yes, dear friends, kindly just observe here. When we just move on, yes, if we just have the case 1 as lambda, which is equal to 3. Okay, so here A minus 3I, which is equal to 1 minus 3, 2, 2, and 1 minus 3. So this is what the exact matrix. And here it is resulted to minus 2, 2 and 2 minus 2. So this exact matrix it comes. And solving the null spaces, kindly just observe, dear friends, minus 2v1 plus 2v2, which is equal to 0. Yes, which implies v1 which is equal to v2. So here a valid eigenvector, we just get it as like, yes, V which is equal to 1 and 1. And when on normalizing, yes, it just comes 1 divided by root 2 multiple of this matrix. And when with verification, yes, dear friends, so we have A multiplied by V, which is equal to 3 and 3. Yes, yeah, it is what the 3V. So we are just getting that particular functionality by using this lambda 1, which is equal to 3. So let me just compute the shifted matrix by using the case 2 functionalities. Yes, here the case 2, which is lambda, which is equal to minus 1. So let me just make use of it and identify. So see here, dear friends, so A minus of minus 1 into I. So here we just get A plus 1, which is equal to 2, 2, 2 and 2. This is the matrix. And yes, by using the null space, yes, from the first row, we just get 2v sub 1 plus 2v sub 2, which is equal to 0. Yes, which it is implies v1, which is equal to minus v2. So a valid eigenvector here, V, it would be 1 and minus 1. And when on normalizing, yes, we just get 1 by root 2 of matrix 1 and minus 1. And kindly just observe the verification, dear friends. So here we just get AV, which is equal to minus 1 and 1. So yes, resulted towards minus 1 multiple by V. So yes, that is what we are just getting it here. So this is for the case 1 and kindly just observe, and this is for the case 2 functionality, and we just, when we apply towards the first row with the null space, here we just get, and when on verifying, kindly just observe, when on verifying, yes, we are able to get, yes, both, or yes, it's equal. And towards with the geometric interpretation, yes, kindly just observe, dear friends, when we just go towards this verification of numpy eigenvalues, yes, dear friends, here when we just make use of this eigenvalue by using 1 and 1 the transpose, yes, it directions along the line y is equal to x. And it is stretched by factor 3. So that is what the first lambda which we have observed. Okay, first case study. And second is we just had the exact functionality as like eigenvalue, which is 1 and minus 1 the transpose. So here the direction along the line y, which is equal to minus x, and here reflected and scaled by factor minus 1. So that is what we just got it here. Yes, the lambda 2, the factor, it is minus 1. Dear friends, by this code, yes, this exact code demonstrate the canonical procedure. Yes, first it just compute the eigenvalue, and for each eigenvalue from A minus lambda I, yes, it solves its null space, and then normalize the resulting vector, and it just verifies that is A multiple by V, which is equal to lambda multiple by V. And here, comparing with the numerical routines, it explicitly shows the eigenvector arise as non-trivial solutions to a homogeneous linear system, making to connection between eigendecomposition and null space fully concrete. Okay, now let we just have a practice, that is we use an linear algebra for eigendecomposition rather than computing eigenvalues and eigenvector by hand. So the function returns both the eigenvalues as a vector, okay, and the eigenvector as columns of a matrix. So yes, dear friends, this script demonstrates the practical computation and correct interpretations of eigendecomposition in NumPy, with an emphasis on a common source of confusion, that is how eigenvectors are stored. Okay, so here we just start with defining a matrix. Yes, here we are just going to have our matrix A, which is 1, 2, 3, and 4. And yes, let me just define the eigendecomposition via NumPy. Okay, so this NumPy returns eval, that is array of eigenvalues, that is lambda 1 and lambda 2. And here we have the matrix whose columns are eigenvector, and here we just get that, so A multiple by V, which is equal to V multiple by A. So here V, actually it is what the eigenvector, that is columns, and A, yeah, it is the diagonal matrix of eigenvalue. Next, we are going to have our critical structure details. Yes, eigenvalues are according towards the column. So here we just get this exact column. Yes, we just get the first eigenvector, and here we have the second eigenvector, and this is essential. Yes, when we just go towards that ith eigenvector, and here we are just making it towards the column. Yes, dear friends, kindly just observe, this is a column conversion, because the matrix equation is, kindly just observe, A multiple by V1 V2. Okay, so here which is equal to that V1 V2 multiple by lambda, that is lambda 1 and 0 lambda 2. So here each column satisfy A multiple by V sub I, which is equal to lambda sub I multiple by V sub I. And kindly just see here, dear friends, this one here, a common mistake explicitly shown. Yes, this one, it is a column, not an row. Because row makes components of different eigenvectors. They do not satisfy A multiple by V, which is equal to lambda multiple by V. And here we have the loop functionality for verification. Yes, for each eigenpair, it's just going to compute two things. Yes, one, it is as like A multiple by V, and next one, it is lambda multiple by V. So it just compare using this NumPy functionalities also. So this validates the defining equation as like A multiple by V, which is equal to lambda multiple by V. And dear friends, here we are just having the alclose, so which is used instead of exact quality, because floating point arithmetic introduces small rounding errors. And here we are just going to have the results typically match up to 10 to the power of minus 8 precision. So let me just execute and view the output. So this code operationalize the exact factor. Kindly just observe, dear friends, this eigenvalues, yes, it is a scaling factor. And eigenvectors, yes, of course, invariant directions. And here the matrix A acts as stretching along eigenvector direction with a different scaling factor as per direction. And dear friends, again I just specify here the single most column mistake when working with eigenvector in code is confusing rows and columns. And here NumPy exactly stores the eigenvectors as column of a matrix, not rows. So with square matrix, you will not get a shape error if you accidentally use rows. So you just get wrong answer silently. And here always access eigenvalues as a column slicing, not a row slicing. So this convention follows from the standard mathematical notations where V, of course, it is what's an eigenvector, computes a column of V. So yes, dear friends, exactly this script, it just summarizes that here we are just getting from this, yeah, we are returning the eigenvectors in columns. So each column corresponds to one eigenvalue. So the verification loop confirms the eigendecomposition numerically. And misinterpreting rows as eigenvector is a fundamental but common error. Script reinforce both the correct API usage and the underlying linear algebra structure. And dear friends, here we are just going to discuss on an important topic. Yes, eigenvectors are not unique. If V is an eigenvector of A, then alpha multiple by V is also an eigenvector for any non-zero scalar alpha. And here, of course, here we have the exact proof. A multiple by alpha V, which is equal to alpha multiple by AV. So here, which is equivalent to alpha multiple by lambda V, and which implies lambda multiple by alpha V. So if V is an eigenvector, any scaled version of V is also an eigenvector. That is what here it is specified. Okay, let me just discuss that by using the code. So this exact script demonstrates a fundamental properties of eigenvector. So they are not unique in magnitude or sign, only in direction. So here we are just starting the defining matrix. So kindly just observe, dear friends. So this one, it is the matrix A. We have 1, 2, 2 and 1. And of course, kindly just observe this functionality, which is just shows V1 is one eigenvector corresponding to the eval of 0. And here NumPy returns eigenvector normalized to unit vector length. So in such a case, norm factor of V sub I, which is equal to 1. And dear friends, kindly just observe here we just specify mathematical principle as like A multiple by V, which is equal to lambda multiple by V. So therefore for any scalar, that is alpha which is not equal to 0. Yes, as I have already specified, A multiple by alpha V which is equal to alpha multiple by AV, and which it implies as alpha multiple by lambda V, and yes, which is equal to lambda multiple by AV. And yes, AV is also an eigenvector. And kindly just observe, dear friends, here this exact code demonstrate for each scalar alpha, the code exactly computes this loop functionalities. Yes, it just verifies, and it was specified as with all close functionalities. Okay, and here it just proves that is each output line conforms towards this functionalities, that is A multiple by alpha V which is equal to lambda multiple by alpha A. So here the eigenvalue equation still holds after scaling. So let me just execute and view the outputs. And here we are able to witness one thing. Kindly just observe alpha which is equal to -1. Yes, V which is implies to -V. So the vector points in the opposite direction but still lies on the same line through the origin. So here that implies that V and -V represents the same eigen direction. And here I just want to specify one thing, dear friends. Here eigenvalues, and here we have the geometric interpretation. Yes, eigenvector defines lines in one-dimensional subspace, not specific arrows. And here it just transformations A, that is it preserves the line, scales vectors along it, and yes, of course, by this we are able to specify that span of V which is equal to, yes, alpha V when alpha belongs to R. And here normalization is used. Yes, numpy returns unit vector because removes arbitrary scaling ambiguity and makes comparisons consistent, and it improves numerical stability. But mathematically normalization is a convention, not a requirement. And yes, finally we have the statement. Yes, kindly just observe, direction matters, magnitude and sign do not. So this is exact practice. Eigenvectors are defined up to non-zero scalar multiples. The only invariant properties is their direction, that is the span. And yes, dear friends, this exact code just verifies that scaling an eigenvector by any non-zero scalar produces another valid eigenvector. So the eigenvalue equations remain satisfied. Eigenvector represents directions, not fixed vectors. So this property is essential for correctly interpreting eigendecomposition in both theory and practice. Dear friends, let me discuss diagonalizing a square matrix. Each eigenvalue and eigenvector pair gives us one equation. Yes, mathematically it is A multiple by V sub I which is equal to lambda sub I multiple by V sub I. For an M into M matrix, we have M such equations. We can combine them all into a single elegant matrix equation. Now let's collect all eigenvector as column of matrix V and all eigenvalues in a diagonal matrix of lambda. So with this, observe, let me just have a matrix as like. Here if we have A multiple by V matrix, that is eigenvectors. So here it would be V1, V2, V3 till Vm matrix. And this would be equal to, yes, as such, V1, V2, V3 till Vm. This is the vectors, and here the eigenvalues in a diagonal matrix. So lambda 1, 0, 0 till to the last column, and 0, lambda 2, and 0 till to the last column. Yes, as such we have 0 till lambda m. This is what our V eigenvectors, and this is what the lambda eigenvalues. So this gives us, yes, A multiple by V which is equal to V multiple by lambda. The magic of diagonal matrix on the right. Yes, when V is post multiple by this lambda, each column of V gets scaled by the corresponding diagonal entry, and here column I, of course, of V is multiple by all these lambda I. Exactly. what the eigenvalue equation says. And here, when on just rearranging, kindly just see here dear friends, when on just rearranging, if I just go for V, which is equal to V multiple by lambda multiple by V inverse. And dear friends, this is called the eigendecomposition or diagonalization of A. So it decomposes the matrix into three factors. One, a changes of basis, that is V inverse, a simple diagonal scaling lambda, and the inverse changes of the base V. And dear friends, in the standard basis, A is a complex matrix with entries everywhere. But from perspective of an eigenvector basis, A is simply a diagonal matrix. All it does is a scale each axis independently. And here the eigendecomposition reveals the natural coordinate system in which the matrix has the simplest possible form. Let me just discuss by the code. Kindly just observe here, dears. This exact script demonstrates matrix diagonalization, verifying both the forward relation A multiple by V, which is equal to V multiple by lambda, and the reconstruction form, that is A, which is equal to V multiple by lambda and multiple by V inverse. So here let me just define the matrix. So here A is a 2 into 2 matrix, and here we have the eval and ecalc, that is eigenvalue lambda 1 and lambda 2, and here eigenvector, that is matrix V, whose columns are eigenvectors. And dear friends, kindly just observe, here is the constructing of the diagonal matrix. So this matrix contains only scaling factor along its diagonal. So when we just do lambda, yes, we just get lambda, which is equal to lambda 1, 0, 0 and lambda 2. So this is what the exact. So this matrix contains only scaling factors along a diagonal. So here it is what the core identity, that is AB, which is equal to V multiple by lambda. So when we just make it mathematically, kindly just observe, V, of course, we have two vectors, V1 and V2. And if we just multiple by A, so here we just get AV1 and AV2. Using the eigenvalue property, kindly just observe AV sub I, which is equal to lambda sub I multiple by VI. This would be happens as like AV, which is equal to lambda 1 V1 and lambda 2 V2. Actually, this is what V multiple by lambda. And dear friends, kindly just observe this exact left hand side, which we just have this. Yes, apply transformation to each eigenvectors. And each right side, yes, it just scales eigenvector. So this produces the same result, confirming that AV, which is equal to V lambda. And coming towards the reconstruction, kindly just observe, dear friends, when on just reconstructing, yes, what we just have is A, which is equal to V multiple by lambda multiple by V inverse. So here we are just changing the basis and we are just going to scale it and change back with the V. Yeah, we are just going to have this. And actually why this works is, yeah, when on just making towards this particular, kindly just observe, dear friends, if we just have, this is what the base. Okay, so this is what the base. If we multiple both the sides by V inverse, what happens? So this V and multiple by V inverse. So here we just have A and V lambda V inverse. Here diagonalizing decomposition at transformation into 3 steps. Yes, we want to check whether we have any rotation, that is changes coordination is there or not. Yes, that is done by V inverse. Do we have any scale independently along the principal direction? Yes, that is what the lambda. And transform back to the original basis. Yes, that is what the V, the eigenvectors. And for verification, yes, we are just going to have this all closed. Yes, we are just going to have, yeah, both the things, that is A multiple by V, which is equal to V multiple by lambda. This is one. And yes, the second one, A, which is equal to V multiple by lambda multiple by V inverse. So numerical tolerance is required due to floating point arithmetic. So yeah, we are just going to discuss this. Let me execute and view the output. So kindly just observe, dear friends, this is what our matrix A, and here we just identifying the eigenvalues. When we just have towards the eigenvectors v, when on multiplying the both, yeah, we just get with a lambda function, that is diagonal matrix lambda function. On verifying, kindly just observe the resultant of A multiple by V, which is equal to V multiple by lambda. So both are equal. Yes, of course it is true. And even on reconstruction, kindly just observe, dear friends, A which is equal to V multiple by lambda and multiple by V inverse. So here that too we just get the same exact matching. So this is what the resultant, and we just have our original A. So both are equal. And dear friends, kindly just observe, dear friends, this exact functionality has three equivalent forms of diagonalization. Yes, starting from this A multiple by V, which is equal to V multiple by lambda, we can rearrange to get these three equations. So that is A multiple by V, which is equal to V multiple by lambda, and A which is equal to V multiple by lambda multiple by V inverse, and lambda which is equal to V inverse multiple by A and multiple by V. So here kindly just observe the second form. This exact decomposes the matrix into its eigen structure. And here the third form, yes, it shows that A becomes diagonal when we transform it into the eigenvector basis. This is why the process is called diagonalization. The matrix A is dense and complicated in the standard basis, but diagonal and trivial in its eigen basis. Dear friends, the eigenvector form a new coordinate system. That is, V inverse converts the vector from the standard basis to the eigenvector basis. So in this new coordinate system, the matrix A is diagonal. It simply stretches each axis by corresponding eigenvalue. Then V converts back to the standard basis. So matrix multiplication by A is fundamentally just stretching along M independent directions. So yes, dear friends, this exact code verifies two fundamental identities. Yes, the one, it is A multiple by V, which is equal to V multiple by lambda. And the decomposition, that is A which is equal to V multiple by lambda multiple by V inverse. So it shows that a linear transformation can be understood as a change of basis into eigenvector coordinates and independent scaling along those directions, and a transformation back to the original space. So this is the core structural insights behind eigen decomposition. Okay, now let me just discuss on symmetric matrices. Symmetric matrices, that is A which is equal to A transpose, have two remarkable properties for eigen decomposition. Yes, that makes them the rock star of linear algebra in data science. Difference property 1, yes, all eigenvectors are pairwise orthogonal. Yes, that is what the perpendicular. And property 2, yes, all eigenvalues are real valued. That is no complex number. Difference, these properties are not shared by general non-symmetric matrices. They make symmetric matrices much easier to work with and give their eigen decomposition a beautiful geometric structure. Let me just discuss this directly by the coding. So kindly just observe, dear friends. Yes, this exact script demonstrates a central theorem in linear algebra. Yes, real symmetric matrices have orthogonal eigenvectors and admit an orthogonal diagonalization. Here matrix R, yes, it is an arbitrary 3 into 3 integer matrix, and here we just specified A which is equal to R transpose R. And towards this properties of construction, yes, the first one, it is all about the symmetry. Yes, kindly just observe here A which is equal to R transpose R. That is what here we just define it. But when on just going for symmetry, yes, kindly just observe it is A transpose which is equal to R transpose multiple by R the whole transpose. So which is equal to R transpose multiple by R, which is equals to A. So here the second one, it is all about positive semi-definite. Yes, kindly just observe, dear friends, here we are just going to take the X transpose multiple by A multiple by X, and here, yeah, with the same thing, kindly just observe X transpose multiple by R transpose multiple by R multiple by X. So which is equal to norms of R multiple by X towards the square Yeah, greater than or equal to 0. So here this exact A is guaranteed to be symmetric with real non-negative eigenvalues. And let me just move on here to define the eigendecomposition. Yes, dear friends, here we are just defining the eigenvalues which are real, and eigenvectors, yeah, can be chosen orthonormal. Okay, and let me just move on here for orthogonality check. Yes, this is the loop for orthogonality check, and here this exact dot functionality, yes, this computes that V transpose V. So kindly just observe V transpose V, which is equal to identity. So here this one we are just expecting it from the eigenvalues and vectors. Kindly just observe. So with I and J functionality, so we are just going to have V sub I the transpose multiple by V sub j. And here the exact expected value, it would be V sub I transpose multiple by V sub j, which is equal to, so if I which is not equal to j, so it would be 0, and if I which is equal to j, that would be 1. And yes, if it is normalized, and here we just get the resultant to be 10 to the power of minus 16, so indicates numerically 0. And kindly just observe, dear friends, here we are just going to have our matrix orthogonality. Yes, for checking matrix orthogonality, V transpose V, which is equal to identity. So yes, dear friends, so this is what? So if eigenvectors are normal, V transpose V, which is equal to identity. So this means columns are mutually perpendicular and each has unit length. And yes, here we just go for an orthogonal matrix V. So here we are just going to specify as like V inverse, which is equal to V transpose. So this is computationally significant. Okay, so let me just execute. So yes, here we have the exact A, and yes, it is a symmetric. Yes, of course it is a symmetric, and it is real. And when we just go towards the eigenvalues, yes, here also we just get a real and non-negative eigenvalues. And towards the eigenvectors, yes, we just get an orthonormal functionality. And when we just make the pairwise orthogonality check, so by using this V sub I transpose multiple by V sub j, yeah, we are just having the orthogonality check, and kindly just observe the exact values. And as I have already specified, yes, it would be an 10 to the power of minus 16. That indicates numerically 0. And if I is not equal to j, it would be 0. And if I is equal to j, so we just get 1. And kindly just observe the V transpose multiple by V. Yes, here it is an identity. So that is also, we are just getting it as like a matrix orthogonality. And yes, it's V is an orthogonal. Yes, of course it is done. And observe one thing, dear friends. Here we are having a huge practical implement. That is when we just make it as like V inverse, which is equal to V transpose. Yes, that's it, true. Because this is computationally significant, and here transpose is far cheaper and more stable than inversion. I have already specified. And how this is happening? Yes. So kindly just observe, dear friends, here when eigenvectors are orthogonal and unit normalized, the eigenvector matrix V is an orthogonal matrix. That is meaning V transpose V, which is equal to I, and therefore V inverse, which is equal to V transpose. And we have already discussed previously, yes. And orthogonal diagonalization, yes, instead of A which is equal to V multiple by lambda multiple by V inverse, yes, we can get the stronger result as like A which is equal to V multiple by lambda multiple by V transpose. And dear friends, kindly just observe, this is called the spectral theorem. And why is such a big deal is, yes, dear friends, actually computing a matrix inverse is expensive. So when we just say, yes, big O of m cube, yes, operations and numerical unstable. A transpose is essentially free. You just swap row and column indices. And here for symmetric matrices, we never need to compute V inverse. We simply use V transpose. This is faster, more stable, and more memory efficient. And in data science, the matrix we eigendecompose are almost always covariant matrices, which are symmetric by definition, as like kindly just observe C, which is equal to X transpose multiple by X. So this simplification applies to virtually every PCA computations you will ever run. So if you know your matrix is symmetric, instead of this, kindly just use, of course, np.linearalgebra.eigh of A. Because here H stands for Hermitian. That is the complex generalization of symmetric. And here this EIGH, yes, this is very faster, more numerical stable, and returns eigenvalues stored in ascending order. Like here I just give you a proof also, dear friends. Kindly just observe. See, this is one of the most important proof in applied linear algebra. Let us walk through in step by step. So as we have already given, yes, kindly just observe A, which is equal to A transpose with the two distinct eigenvalues, that is lambda 1 and lambda 2. Okay, and here kindly just observe this lambda 1 which is not equal to lambda 2 and their eigenvectors v1 and v2. So here our exact goal is we have to specify, that is v1 transpose multiple by v2 which is equal to 0, that is an orthogonal. So let me just start with step 1. So start from the eigenvalue equation for v1 and left multiple by v2 transpose. So here kindly just observe lambda 1 v1 transpose and v2 which is equal to A multiple by v1 the whole transpose multiple by v2. So here what happens? So v1 transpose A transpose multiple by v2. Because of A is symmetric, we already know A transpose which is equal to A. So we can replace A transpose with A and then use the eigenvalue equation for V2. So kindly just observe. So V1 transpose A transpose V2 which is equal to V1 transpose A V2. So here what we just get? V1 transpose multiple by lambda 2 v2, and kindly observe the exact resultant is lambda 2 v1 transpose and v2. Now here combining this first step and second step, lambda 1 here and this is lambda 2. Okay, so we are just going to equalize the both one. So the third one here, it is lambda 1 v1 transpose v2 which is equal to lambda 2 v1 transpose v2. So yes, this implies lambda 1 minus lambda 2 the whole v1 transpose v2 which is equal to 0. And yes, since lambda 1 and lambda 2 are not equal and the factor lambda 1 minus lambda 2 which is not equal to 0, okay, therefore v1 transpose multiple by v2 which is equal to 0. So that makes this proof work is the substitution, that is A transpose which is equal to A. That is what we have just done in the step 2. And for a non-symmetric matrix, A transpose is not equal to A and the chain of equalities breaks. So this is why non-symmetric matrix do not have orthogonal eigenvalues in general. So by this, yes, this exact code verifies that for symmetric matrices, eigenvectors are orthogonal. And here V transpose V which is equal to identity, and here V is an orthogonal. And next one, V inverse which is equal to V transpose. And diagonalizing simplifies, kindly just observe A which is equal to V multiple by lambda multiple by V transpose. So this is one of the most powerful structural result in linear algebra. So turning matrix transformation into independent scaling along perpendicular direction. And here is the second special property, that is symmetric matrix always have real valued eigenvalues. So yes, generally non-symmetric matrix can have complex valued eigenvalues. So even if the matrix itself contains only real numbers. Yes, dear friends, directly let me just go to the code, and yes, this script contrasts non-symmetric versus symmetric matrix in terms of their eigenvalues, and empirically verifies a key theorem, that is real symmetric matrix always have real eigenvalue, whereas non-symmetric matrix may have complex eigenvalue. Okay, so here kindly just observe, let me just go to define as a non-symmetric matrix A, and here we just go with an functionality that confirms the matrix is not symmetric. Not symmetric, yes, of course, as we have already seen previously, that is non-symmetric, that is A which is not equal to A transpose. Okay, and next we are just having the eigenvalue computation. Yes, this produces eigenvalues that may include complex number. And here is the exact key observation. Kindly just observe, dear friends. So this exact functionality returns false. That is, not all eigenvalues are real. And here we have the complex conjugation pairs, and yes, dear friends, for an real valued matrix, complex eigenvalues must appear in conjugate pair. If lambda, which is equal to a plus bi, so is an eigenvalue, then lambda bar, which is equal to a minus bi, yes, is also an eigenvalue. So this arises because the characteristic polynomial has real coefficients. And here we have the exact symmetric versions of the matrix. Okay, so asim, which is equal to, and here kindly just observe, we are going to return true, matrix is symmetric. Okay, so that is also here it is specified. And when on evaluating this also, kindly just observe, there is also going to return true because all eigenvalues are real. Okay, let me just see when on execution. So here we have an empirical verification, that is by using Monte Carlo test, and here this exact loops just generate the symmetric matrices via S, which is equal to R transpose multiple by R. So here it is the properties as like symmetric and positive semi-definite. And yes, of course, kindly just observe, dear friends, this exact line, yes, it just makes the check of eigenvalues. It confirms all eigenvalues are real, and here all 1000 symmetric matrices have real eigenvalue, and it is going to return the true. Okay, so let me just execute. So here on execution, kindly just observe, dear friends. So this is what the non-symmetric. Okay, it just may have complex eigenvalues, non-orthogonal eigenvectors, even defective cases, that is non-diagonalizable. And here when we just go towards the symmetric matrices, yes, for real symmetric matrix A, all eigenvalues are real. Eigenvectors can be chosen orthonormal, and matrix is orthogonally diagonalizable. Yes, of course, orthogonally diagonalizable, it is as like A, which is equal to V multiple by lambda multiple by V transpose. And here for symmetry, it just forces a real eigenvalues. So kindly just observe, dear friends. Here for symmetric A, lambda, which is equal to V transpose multiple by A multiple by V divided by V transpose multiple by V. So here right hand side is always real, so therefore eigenvalues must be real. And dear friends, kindly just observe, here we are going to have a non-symmetric cases. Yes, transformation can include rotation, shear, and this can produce complex eigenvalues. And yes, dear friends, with this symmetric cases, here transformation is pure scaling along orthogonal directions, no rotational component, and hence eigenvalues remain real. So this exact code demonstrates non-symmetric matrices that they produce complex eigenvalues. Complex values occurs in conjugate pair. And when coming towards symmetric matrices, always have real values, that is real eigenvalues, or structural well behaved, and here empirically 1000 symmetric matrices are all real eigenvalues. So this distinction is foundational for understanding when eigendecomposition yields stable interpretable results. Okay, now let me just discuss on singular matrix. Dear friends, a common misconception is always there. That is, learner sometimes think that singular, that is non-invertible matrices cannot be eigendecomposed. This is completely wrong. Eigendecomposition works perfectly well on singular matrix. And here the special property is that at least one eigenvalue is guaranteed to be zero. Think about why. See, singular matrix has a non-trivial null space, meaning there exists a non-zero V. So such that AV which is equal to 0. And comparing with AV which is equal to lambda V, we see that this lambda which is equal to 0 and V is the null space vector. So that we just get this exact equation. Yes, conversely, if all eigenvalues are non-zero, the matrix must be full rank, that is invertible. Let me just discuss this by using the code. So here, yes, this exact script analyzes the eigendecomposition of a singular matrix and connects eigenvalue, rank and linear dependency. Let me just start defining the matrix A, so which is 1, 4, 7, 2, 5, 8 and 3, 6, 9. Okay, and here we are defining the rank and the determinant, and kindly just observe here of course we have a 3 into 3 matrix, but this rank, it won't be out of 3. Okay, let me just see, and let me just determine what is the determinant 2. And dear friends, kindly just observe here we are just defining the eigenvalues and eigenvector. Yes, of course, typically eigenvalues, one eigenvalue would be 0, and here two eigenvalues are non-zero. And yes, dear friends, here we just going to have the null space via eigenvalue for lambda which is equal to 0. So this extracts the eigenvector corresponding to the lambda which is equal to 0. And here we are just going to have the verification. Yes, that exact verification, this confirms AV which is equal to 0. And kindly just observe, dear friends, here we are just having the linear dependency of the column. So here the exact code that inspects the relationship between the columns, and here of course kindly just observe 2 into column 2 minus column 1, yes, which equals the column 3. Okay, so yes, columns are linearly dependent, so this explains rank deficiency and existence of an non-trivial null space. So kindly just observe, dear friends, on execution. So yes, here we have the matrix A. Okay, and kindly just observe the rank, it is 2, and here determinant it is 0. Yes, it just says A is singular, that is non-invertible. And when we just come towards this eigenvalues, yes, kindly just observe, yes, one eigenvalue is 0. So two eigenvalues are non-zeros. Okay, so kindly just observe that. And this exactly specifies that, kindly just observe, a matrix is singular if and only if the determinant of A which is equal to 0. And we have already discussed an product of eigenvalues, that is a product from I which is equal to 1 to m of lambda sub I which is equal to determinant of A. So here if the determinant is 0, at least one eigen must be 0. So yes, dear friends, that is what here determinant is 0 and we have one eigen is 0. And when coming towards this null space eigenvector, so for a lambda which is equal to 0, yes, here we just verify that is A multiple by V which is 0. So this eigenvalues lies in the null space of A. And when coming towards this linear dependency of columns, kindly just observe, dear friends, as I have already specified, here it just indicates to column 3 which is equal to 2 multiple by column 2 minus column 1. So here, yes, these are columns are linearly dependent, and this explains that rank deficiency and existence of non-trivial null space. This exact interpretations of null vector, of course, kindly just observe. So for an example, if we have v as like x, y, z, and yes, then if we just go towards the a multiple by v, so here it would be x multiple by column 1 plus y multiple by column 2 and plus z multiple by column 3, which is equal to 0. So here the exact v encodes the exact linear combination that cancels out. And when coming towards this rank functionality, kindly just observe, dear friends, here as I have already specified, there is a key rule, that is rank of A, which is equal to number of non-zero eigenvalue. So here counting multiplicity for diagonalizable cases. So here kindly just observe, when on just making the matrix maps of R3 into 3, here the rank equal to 2. So image is a 2D plane. And here one direction is completely collapsed, and that direction is the null space, that is AV, which is equal to 0. And here important things is, while the rule holds here more precisely, that is rank which is equal to number of non-zero singular values. For symmetric or diagonalizable matrix, this aligns with non-zero eigenvalues. And dear friends, kindly just observe one important functionalities. Yes, if we just the script establish the chain, that is linear dependency, which is equal towards rank of deficiency, and which would be equal to determinant of A, which is 0, and which implies lambda, which is equal to 0. So a non-trivial null space occurs. And yes, dear friends, this exact script, yes, summarize the matrix, yes, is a singular because its columns are linearly dependent. This guarantees at least one zero eigenvalue, and the corresponding eigenvector is a null space vector. And rank equals the number of independent directions preserved by the transformation. So this example concentrately ties together with eigenvalues, null spaces, rank, linear dependency into a single coherent picture. And towards this, let me just have a summarization that relationship between the matrix, that is eigenvalues, between matrix rank and eigenvalues. So here, if a matrix is a full rank or invertible, then all of its eigen are non-zero. For an example, if the eigenvalues are as like 3 and -1, neither is 0, so the matrix is full rank. On the other hand, if the matrix is rank deficient or singular, then it has at least one eigenvalue equal to 0. So here for an example, the eigenvalue 5 and 0 indicate that the matrix is singular. And more generally, if the rank of an m by n matrix is less than its maximum possible rank, the matrix has 0 eigenvalues corresponding to its rank deficiency. So for an example, consider a matrix of size 3 with rank 2. So its eigenvalue could be 10 or -1 and 0. So the presence of the 0 eigenvalue indicates that the matrix is singular. Let me discuss on quadratic form and definiteness. Dear friends, we arrive at one of the most practical important concept in eigendecomposition. Yes, definiteness. It sounds intimidating, but the idea is simple. Okay, towards the quadratic form, dear friends, kindly just observe. Let me have a given square matrix A. Okay, so and any vectors W. Okay, so here of compatible size. So the quadratic form of this would be, kindly just observe, Q, which is equal to W transpose multiple by A multiple by W. This takes a matrix and a vector and produces a single scalar Q. The question is, what is the sign of Q for all possible vector W? Let us connect this to eigenvalue. Using the eigenvalue equation, of course, we all know A multiple by V, which is equal to lambda multiple by V. and left multiplying by V transpose, what we just get? Yes, V transpose multiple by A multiple by V, which is equal to V transpose whole multiple by lambda multiple by V. So which is equal to, kindly just observe, lambda multiple by V transpose multiple by V. So kindly just observe, dear friends, this would be the V norms of square which is greater than 0. So here, yes, the quadratic form would be lambda multiple by norms of V norms of the square. And here, since this V norm, the whole square, is always positive, we exclude V is equal to 0. So the sign of quadratic form is determined entirely by the sign of the eigenvalue. And because any vector can be written as a combination of eigenvectors, the sign of all eigenvalues determine the possible sign of quadratic form for any vector. Okay, let me just discuss that by the code. So kindly just observe, dear friends. So this script illustrates the relationship between the eigenvalues and definiteness of a matrix via quadratic form. And yes, we already have discussed. So here the quadratic form of Q of W, which is equal to W transpose multiple by A multiple by W, and verifies the theory empirically using random vector. So here kindly just observe, dear friends, we are just going to define the quadratic form definition as symmetric matrix A, and yes, here it is what the defined one, and yes, this has an array as like a 2, 1 and 1 and 3, and we are just defining the eigenvalues. So both eigenvalues are positive. So kindly just observe, when we just make use of this lambda 1, which would be greater than 0, and lambda 2, that also would be greater than 0. And theoretically, of course, if all eigenvalues are positive, we always may specify as like W transpose multiple by A multiple by W, that would be greater than 0. So A is positive definite. And when we just do towards that empirical test, here evaluated values for 10,000 random vectors, and here minimum value is still positive. And yes, dear friends, this exact loop confirms that no direction produces a negative or 0 value. So the quadratic form defines a strictly convex surface. And on to the result, yes, kindly just observe, dear friends, the quadratic form is a elliptic bowl and every direction curves upward. And here no flat or downward directions would be there. Okay, let we have an second example, so which is just specify an indefinite matrix. So here we have that indefinite matrix -1, 2 and 2, 1, 1, and of course we are going to have the eigenvalue for this indefinite matrix. Yes, when we just describe this, one eigenvalue would be positive, another eigenvalue would be negative. So yes, dear friends, so for an indefinite functionality, lambda 1, that would be greater than 0, and lambda 2, that would be less than 0. And if eigenvalues have mixed sign, here W transpose multiple by A multiple by W can be positive or negative. So here A is indefinite. And here we have the empirical result. Yes, minimum is negative, maximum is positive. So this exactly confirms some direction produce positive curvature, other produce negative curvature. So here this exact in quadratic form is a saddle surface, and curves upward is some direction, downward in another directions. Okay, so let me just execute and identify the resultant. So here we have the exact positive definite, and here we have the indefinite matrix. And kindly just observe, dear friends, we are just determining the sign of eigenvalues by using the diagonalization. Yes, for diagonalizing, kindly just observe, if A, which is equal to V multiple by lambda multiple by V transpose, then here we just get W transpose multiple by A multiple by W, which is equal to V transpose multiple by W, the whole transpose multiple by lambda, and for V transpose here V transpose and multiple by W. So let Z which is equal to V transpose multiple by W. Then what we just get? Yes, kindly just observe W transpose multiple by A multiple by W, which is equal to summation of I of lambda sub I multiple by Z sub I square. So each term is weighted by an eigenvalue. Since here Z sub I the square that is greater than or equal to 0. So that the sign depends entirely on this lambda sub I. And dear friends, kindly just observe. So with this we are just identifying the eigenvalues. And if all eigenvalues all greater than 0, so definiteness would be positive definite. And if all the eigenvalues are less than 0, it would be negative definite. But if it has a mixed sign, yes, surely it is an indefinite functionality. And kindly just observe, dear friends, if it is greater than or equal to 0, that is some zeros would be there, na? So in such a case it would be semi-definite functionality. So here with this functionality, yes, here we just get, yes, positive definite, it is an unique minimum, and indefinite, so we just get a saddle point. And dear friends, kindly just observe in machine learning, yes, Hessian matrix determines curvature, and with using the numerical method, yes, positive definite matrices enable efficient algorithm. And yes, dear friends, this exact code just demonstrate positive definite matrix. So all eigenvalues here are positive, and quadratic form always positive, and here the geometry would be convex bowl. And when coming towards the example 2 as an indefinite matrix, so we just get mixed sign eigenvalue, and here quadratic form can be positive or negative, and the geometry would be saddle surface. So the key identity would be, yes, as we have already discussed, so it would be as like a W transpose multiple by A multiple by W, which is equal to summation of I of lambda sub I multiple by Z sub I square, which explains why eigenvalues completely determine definiteness. Based on the sign of eigenvalue, every square matrix falls into one of the 5 definiteness categories. So positive definiteness, all the eigenvalue, that is lambda sub I, would be greater than 0. And for positive semi-definiteness, that is all lambda sub I would be greater than or equal to 0. So in such a case, some would be 0 also. And when coming towards indefiniteness, yeah, it would have the mixed values of positive and negative. And going for negative semi-definiteness, that is all eigenvalue, that is lambda sub I, that would be less than or equal to 0. And yes, here also some values would be 0. And last but not least, negative definiteness, that is all eigenvalue, that is lambda sub I, would be less than 0. Difference why this definiteness matters in data science or machine learning. It is mainly important for, yes, of course, optimization. Yes, gradient descent requires the loss functions Hessian matrix, that is the matrix of second derivatives, to be positive semi-definite at a minimum. If the Hessian is indefinite, you are at a saddle point, not a minimum. And of course, a covariant matrix, every valid covariance matrix is positive semi-definite. Here, positive definite if the data is full rank. So if you compute a covariance matrix and find a negative eigenvalue, something went wrong in your computation. And next, Cholesky decomposition, that is the first matrix factorization, which is A which is equal to L multiple by L transpose, works only on positive definite matrices. It is used in Monte Carlo simulation to generate correlated random data. Okay, so here let me just visualize the quadratic form, that is Z which is equal to W transpose multiple by A multiple by W. Yes, we are going to visualize this quadratic form as a 3D surface for 3 classes of symmetric matrix. So making definiteness geometric explicitly. So here we are just going to kindly just observe, dear friends, we are just going to create 3D subplots. One is for positive definite, and the next one for indefinite and negative definite. So here we are defining the matrix and the titles. So each matrix is a symmetric, ensuring real eigenvalue, orthogonal principal directions. And here we are having the grid over input space, so that defines the vector. And yes, towards the vector, kindly just observe, dear friends, it would be W, which is equal to W1 and W2. So yes, column wise. So evaluate the quadratic form over a grid in 2 matrices, that is R2. And here we are going to compute the quadratic form. So this is the expanded form of W transpose multiple by A multiple by W. And for symmetric A, this simplifies into A sub 1 1 multiple by x square plus 2A sub 1 2 multiple by xy plus A sub 2 2 multiple by y square. And kindly just observe, dear friends, this exact line, yes, it was for surface plotting. So here height Z represents the exact equation of W transpose multiple by A multiple by W. So here color map enhances curvature visualization. And here we are just going to have the eigenvalues in the title. So it displays eigenvalues for each matrix. So these directly determine the surface space. And here it references the exact plane, that is Z is equal to 0, which provides a baseline to compare sign of W transpose multiple by A multiple by W. So here we have the exact matrix value for positive definite, indefinite and negative definite. So let me just first of all evaluate the exact eigenvalue, and then we visualize the output. So the case A, yes, it is for positive definite. So the matrix A, which is equal to 2, 0.5. So here the exact eigenvalue both would be greater than 0. And yes, the surface here, it just makes a upward opening bowl. That is would be elliptical parabola, right? And entirely above Z, which is equal to 0. So here W transpose multiple by A multiple by W would be greater than 0. And when going on to the second case, yes, it is for indefinite. Yeah, we are having the matrix A, which is equal to -1 and 2 and 2 and 1. So here the exact eigenvalue, one would be positive and another would be negative. So here the surface would be saddle space, that is hyperbolic parabola, right? And here the exact value Z would crosses the plane. The W transpose multiple by A multiple by W would be greater than 0 or less than 0. And towards the case C, yes, we are just going to have the negative definite. Yes, kindly just observe the matrix A, it is -3 is -0.5 and -0.5, and here it is -2. So yes, eigenvalue both would be less than 0, and here downward opening bowl. That surface would be downward opening bowl, and entirely below the Z is equal to 0. And yes, dear friends, here our equations would be, that is W transpose multiple by A multiple by W would be less than 0. Okay, let me just visualize the exact output. So here each surface shows the value of W transpose multiple by A multiple by W as a function of the two element vector, that is W, which has W1 and W2 the whole transpose, and the gray plane makes the Z, which is equal to 0. And here when coming towards this positive definite, kindly just observe difference. The lambda value, it is 1.8 and 3.2. And here the surface forms a upward opening bowl that never touches or crosses the gray plane. No matter which directions you move in the W1 or W2 plane, the quadratic form is always positive. Next, here the indefinite, kindly just observe the lambda value, it is -2.2 and 2.2. So here the surface forms a saddle shape. It curves upward in some direction and downward in other. So the surface crosses the gray plane. Kindly just observe, this is what the gray plane, and meaning that quadratic form is positive for some vectors and negative for others. And last one, it is all about a negative definite. So both lambda, which is equal to the eigenvalue, it is negative, that is minus 3.2 and minus 1.8. So the surface forms a downward opening bowl, always below the grayscale. So this is the plane, okay, and here that is what below the gray plane. So the quadratic form is always negative. This is the maximum analog of positive definite. And dear friends, the eigenvalue determines the shape. So the eigenvalue defines the axis of the bowl, saddle, and the eigenvalue determines the curvature along each axis. So larger lambda means tighter curvature. That's it. So this code turns an abstract algebraic object into a geometric one. So quadratic form, that surfaces in 3D, and here eigenvalue, curvature along principal axis, and here definiteness by position relative to z is equal to 0. So it provides a direct visual proof. That is, eigenvalue signs always relate with global shape of W transpose multiple by A multiple by W. And furthermore, here we have one thing, dear friends, that is always, that is A transpose multiple by A is always positive semi-definite. See, one of the most important fact in applied linear algebra, that is any matrix of form S which is equal to A transpose multiple by A is guaranteed to be a positive semi-definite, and of course positive definite also if A has full column rank. And here we have the exact proof. Kindly just observe W transpose multiple by S multiple by W, which would be, yes, of course, here we are just going to have the squared norms of A multiple by W, that would be greater than or equal to 0. Because this exact, the squared norm of A multiple by W is always non-zero. That is, magnitudes cannot be negative. It equals 0 only when AW which is equal to 0. So which happens only when W is in the null space of A. That is, when A is singular. Difference for every covariance matrix which is computed as like C which is equal to 1 divided by n minus 1 whole multiple by X transpose multiple by X. Here X is the mean centered data matrix. So therefore every covariant matrix would be a positive semi-definite. That is, which is guaranteed, that is all eigenvalue that would be greater than or equal to 0. So variance is never be a negative. And all eigenvalues are real valued. All eigenvalues are orthogonal. And the eigendecomposition is numerically stable. So let me just discuss that by using the code. So here it is what? So dear friends, this exact script verifies a fundamental results in linear algebra. That is, for any real matrix A, the matrix A transpose A is always symmetric, positive, semi-definite, and is positive definite if A has a full column rank. So let me just set up the test cases. So here you are going to evaluate A transpose multiple by A across different shapes and ranks to show the result is universal, not dimension specific. So yes, a tall matrix or wide matrix, a square matrix, and rank deficient. And here we are going to construct the matrix, that is A transpose multiple by A. So here it defines the two main key properties. That one, it is all about the symmetry. Yes, of course, A transpose multiple by A, the whole transpose which is equal to A transpose multiple by A. And second, it is for quadratic form. So kindly just observe X transpose multiple by A transpose multiple by A whole multiple by X, which is equal to A multiple by X whole transpose multiple by A multiple by X. So here, yes, the square norms of A multiple by X, that is greater than or equal to 0. So this immediately implies all eigenvalues are non-negative. And here exactly, kindly just observe, this is what the eigenvalue computation, and here it is eigen H is used because A transpose A is a symmetric. So here it returns real sorted eigenvalues. And here we are just going to have the non-negative checks that allows for small numerical error also. Yes, it just confirms, that is lambda sub I, that would be greater than or equal to 0. And dear friends, kindly just observe this one. Yes, we are just going to detect the definiteness. So here, whether it is a positive definite or positive semi-definite, we are going to observe on execution. And here we are having the exact tall matrix. Kindly just observe. So each cases we are just going to have it, and each cases we have a different matrix formation. So let me just discuss that, and then we just go for the execution. So in on just case A, that is the tall matrix. So it has a 5 into 3 matrix. So likely full column matrix here, it would be, the rank would be 3. And of course for A transpose A, it would be a 3 into 3 matrix, and surely it is a positive definite. And when just going for the B cases, actually it is a wide matrix and it is of 3 into 5 matrix. And kindly just observe, the rank actually it would be less than or equal to 3. And when suppose going for A transpose A, yes, kindly just to see here, it would be a 5 into 5 matrix, and surely it has at least 2 0 eigenvalue. So it would be a positive semi-definite. Next, the case, it is all about a square matrix. Yes, it is a 4 into 4 matrix, and here if it is a full rank, it would be a positive definite, or otherwise it would be a semi-definite. So kindly just keep it in mind. And the last case, yes, it is a ranked deficiency matrix. And here kindly just observe, dear friends, here we are just having a 2 by 3 matrix, and yes, the rank it would be less than or equal to 2. And when going on for A transpose A, yes, it has at least 1 0 eigenvalue, that is positive semi-definite functionality. And here we are just going to have a relation with the singular values also. Yes, dear friends, eigenvalues of A transpose A are, kindly just observe, lambda sub I, which is equal to sigma sub I the square. And here where sigma sub I are a singular values of A. So thus always non-negative, and here 0 eigenvalue would be equalized to 0 singular value, which it just implies the rank deficiency. And here we have the rank relationship. So yes, dear friends, rank of A transpose A, which is equal to rank of A. So number of non-zero eigenvalue would be equal to rank of A. So let me execute. So as here we have already discussed, so kindly just see here, dear friends. So yes, here we have the tall matrix. So the shape of matrix, it is 5 into 3, and here the rank is 3. And when on just evaluating the A transpose A, yes, the shape is 3 into 3, and the eigenvalue, yes, all the eigenvalues are positive. And yeah, it is a category of positive definite. And when just going for this wide matrix, kindly just observe, we just have 3 into 5, and the exact rank, yes, it is exactly 3. And when going for the eigenvalue, kindly just observe, dear friends, we have few zeros also, that is less than or equal to 0. And when just going on towards this square matrix, kindly just observe, dear friends. So here, yes, it is a 4 into 4 matrix, and here we have the rank, it is also 4, and all the exact eigenvalues are positive. And as it is a full rank, we just get a positive definite functionality. So if it is not a full rank, we just get a semi-definite. Okay. So here it is a full rank functionality. And last but not least, the rank deficiency. And kindly just observe the rank, it is 2. And here we have an, of course, at least 1 0 value, eigenvalue here it is. So it is a positive semi-definite functionality. Dear friends, kindly just observe in every test case, the eigenvalue of this A transpose A are non-negative, confirming the proof. When A is full column rank, all eigenvalues are strictly positive. When A is rank definite, some eigenvalues are exactly zero. And here the connection towards the variance is in PCA, the eigenvalues of covariant matrix represents the variance captured by each principal component. A negative variance would be physically meaningless. So it would be like saying yes, the data varies by -3 unit or like that. So here the A transpose A structures ensures this never happens. And one thing, dear friends, not all symmetric matrices are positive semi-defined. So from this, the code empirically confirms that A transpose A is always symmetric, positive semi-definite, and it is positive definite if rank A, which is equal to number of columns. And yes, dear friends, the final takeaway functionalities, surely I have to specify this. Yes, so here X transpose multiple by A transpose multiple by A multiple by X, which is equal to, yes, double norms of A multiple by X, that would be greater than or equal to 0. So this identity is the entire reasons the result holds, and it underpins a large portion of numerical linear algebra and optimization. Okay, dear friends, let me just discuss about generalized eigendecomposition. Dear friends, standard eigendecomposition solves A multiple by V, which is equal to lambda multiple by V. And here, generalized eigendecomposition solves a more general problem, that is A multiple by V, which is equal to lambda multiple by matrix B multiple by V. Here, instead of scaling the eigenvector by scalar, that is lambda V, we are going to scale it by another matrix times a scalar, that is lambda B times V. So the resulting here, the lambda and V vector pair are not eigenvectors of matrix A alone or B alone. They characterize the relationship between both the matrix. So conceptually, you can think of generalized eigendecomposition as a regular eigendecomposition of product of A multiple by B inverse. So though the implementation does not require the matrix B to be invertible, so here actually this is very much useful in data science or machine learning, mainly in Fisher's linear discriminant analysis. Yes, a classification techniques finds the projections that maximize the between class variation relationships to the within class variance. So this is formulated as a generalized eigendecomposition of two covariance matrix. And here the standard requirement is that this exact B, yes, is a positive definite, which is a guaranteed when B is a covariance matrix. Okay, let me just discuss it by code. Kindly just observe, dear friends. So the exact script demonstrates the generalized eigendecomposition problem and mathematically specified as like A multiple by V, which is equal to lambda multiple by B times V for symmetric positive definite matrix of A and B, and verifies its properties numerically. So here we are just going to construct the SPD, that is symmetric positive definite matrices here. And yes, kindly just observe which is a guaranteed symmetric positive definite, because here R multiple by R inverse is always symmetric and positive semi-definite. And this exact matrix, when we just add with, of course, A divided by 10, this ensures a strict positive definiteness B and better numerical conditioning. So here both A and B satisfies, that is X transpose A times X, that would be greater than 0, and X transpose B times X, that would be greater than 0. And here when we just go towards the generalized eigen problem, we define here these eigenvectors and eigenvalues. So yes, this exactly solves, as to the same A multiple by V sub I, which is equal to lambda sub I multiple by B times V sub I. And here kindly just observe, dear friends, this eigenvalue, yes, it is a generalized eigenvalue, and towards the vectors, yes, it is a generalized eigenvectors towards the column. And when we just interpret for this generalized Eigen decomposition, dear friends, kindly just observe, unlike standardized Eigen decomposition, that is AV which is equal to lambda V, this generalized Eigen decomposition measures scaling relative to B. So here we just get lambda which is equal to V transpose A times V divided by V transpose B times V. So this is a generalized Rayleigh quotient. And yes, we are just going to have a verification check, that is here with this loop. Yes, we are just going to have the verification, and by using the lambda functionality, it just going to check the equation A multiple by V sub I, that would equals with lambda sub I B times V sub I. And here, yes, kindly just observe this all close formula confirms numerical correctness. And for symmetric positive definiteness for B, this eigenvector satisfied, that is V sub I transpose multiple by V times V sub j, which is equal to, if I which is equal to j, it would be 1, and if I which is not equal to j, it would be 0. So here eigenvectors are orthonormal under the B, that is inner product, not the standard dot product. Kindly have a note. And when we just go towards the reduction to standard Eigen decomposition, here GED, that is generalized Eigen decomposition, can be converted to a standard problem. So since the exact standard problem for this B matrix, here B which is equal to C multiple by C transpose, that is using Cholesky formula, and here then we are just going to define a tile, that is C inverse multiple by A multiple by C inverse the whole transpose, and we are just going to solve this by A tile multiple by U, which is equal to lambda U, and it just recovers that V which is equal to C inverse the whole transpose multiple by U. And of course we just have this Eigen H, so which performs this transformation internally. And kindly just observe, dear friends, it has a connection to a standard Eigen decomposition. Yes, by using Eigen H. And here kindly just observe, when we have B is equal to identity. Okay, when we just have B is equal to identity, our GED, that is a generalized Eigen decomposition, reduced to A multiple by V, which is equal to lambda multiple by V. And here you can just check this by using this all close functionality, and yes, we are just going to get a generalized solver matches standard Eigen decomposition. And here let I just execute. And dear friends, kindly just observe, this is what the matrix A. Okay, so here it is a symmetric and positive definite, and the matrix B, yes, this is also a symmetric positive definite, and here we just get the generalized Eigen value, and we just have the generalized Eigen vectors towards the column. And when we just interpret with generalized Eigen decomposition, that is GED, yes, here we just get the verification of this, the lambda functionality, that is by using this, yeah, we are having, that is AV, which is equal to lambda B times VI. So here this is what the A, and yes, this one, it just makes the B times V, which both are, kindly just observe, both are equalizing. So this confirms numerical correctness. And when we just go towards the connection to standardized Eigen decomposition, kindly just observe, dear friends, here when B is equal to identity, the GED with this functionality, it also equalizes the exact value. So yes, both are same, and it just confirms generalized solver matches standard Eigen decomposition. And yes, dear friends, by using this code, yes, this exact code demonstrate solving the generalized Eigen problem, that is AV which is equal to lambda multiple by B times V. Yes, verifying correctness numerically and showing equivalence to standard eigendecomposition when B is equal to identity. And here implicitly it using the fact that B defines a metric. Eigenvectors are orthogonal under that metric. And one thing I have to add on, dear friends, so generalized eigendecomposition answers a deeper question that the standard case, that is, in which direction does A dominate relative to B. So this make it fundamental in problem involving ratios of quadratic form, not just absolute scaling. So before we conclude, let us verify two beautiful mathematical relationships that connect eigenvalue to quantities we already know. One, of course, the summation of eigenvalues, and mathematically summation from I equals 1 to m of lambda sub I, which is equals to the trace of A. And second one, yes, the product of eigenvalues, that is the product form of I, which is equals to 1 to m of lambda sub I, which is equal to determinant of A. So let me just have the experimental setup, that is we are just going to have a random square matrix of varying 3 into 3 size and 4 into 4 size and 5 into 5 size. And here eigenvalues may be real or complex. And computation uses floating point arithmetic. And dear friends, kindly just observe here we are just going to have the trace and summation of eigenvalues. That is trace versus summation of eigenvalues, and theoretically it just results trace of A, which is equal to summation of I of lambda sub I. And dear friends, the trace is the sum of diagonal elements, and here always equals the sum of eigenvalues, that is continuing multiplicity. Here we are just having it with a dot real, that is complex eigenvalues occurs in conjugate pair. For an example, let I just give like this. So here A plus BI plus A minus BI, which is equal to 2A. And here imaginary part cancels, so the total is real. And dear friends, kindly just observe this determinant of A and product evaluation. So theoretically it just specify, yes, as I have already specified. So kindly just see determinant of A, which is equal to product of I, which is equal to 1 to m of lambda sub I. So here determinant encodes total volume scaling. Eigenvalues represents scaling along principal director. So product combines these effect. And yes, dear friends, numerically we have, yes, comparison we are just going to have, yes, uses tolerance based comparison due to floating points rounding and numerical eigendecomposition errors. So let me just execute, and when we just go towards this trial one, yes, here we have 5 into 5 matrix and here 4 into 4 matrix. The sum of all the roots, which is equal to the trace, and here the product of the roots, which is equal to the determinant. Actually, this comes directly from the characteristic polynomial of determinant of A minus lambda I. And dear friends, actually from polynomial theory, here the sum of roots, which is equal to trace, and the product of roots, which is equal to determinant. So from that, yes, kindly just observe this is what the trace, and here sum of the roots, which is equal to trace. And yes, we get the determinant of A, and here product of that eigenvalue, that is the roots, which equals the determinant value. So yes, it matches all the same. And yes, dear friends, these properties holds for any square matrix, that is non just symmetric, real or complex matrix, even if matrix is not diagonalizable or eigenvalues are complex. And yes, dear friends, from this we are able to say that is trace totally linear scaling effect. And yes, the trace is a sum of directional stretch factors, and when coming towards determinant, it is total volume scaling effect, and it includes orientation, that is sign. And yes, from the script the confirms experimental that trace, which is equal to sum of eigenvalue, and determinant, which is equal to product of eigenvalue. So these are not coincident but structural invariants derived from the characteristic polynomial, and they remain valid across all square matrix regardless of symmetry or diagonalizability. And that's a wrap, dear friends. Today we explored one of the most elegant concepts in mathematics and data science, We begin with a simple question: what happens when a matrix transforms a vector? And that question leads us into the fascinating world of eigenvalues and eigenvectors. We have discussed eigenvectors as special directions that remains unchanged in orientation. Eigenvalues tells us how much those directions stretch or shrink. And here the most important lesson is, yes, eigendecomposition is not about matrices. It is about finding hidden patterns. When data becomes complicated, eigenvector reveals the important direction. When data set becomes high dimensional, PCA uses eigenvector to simplify them. When noise hides useful information, eigenvalues help separate signals from noise. So that's why eigendecomposition powers PCA, machine learning, computer vision, signal processing, network analysis, financial modeling, scientific computing. Of course, dear friends, every time a machine learning model discovers hidden structure in data, eigendecomposition is often working quietly behind the scenes. I hope I think so this session would be very much useful. Yes, dear friends, the true power of mathematics lies not in solving equation, but in discovering the hidden patterns behind them. So thanks for watching. See you in the next session, dear friends. Happy learning.